And again, I'm going to emphasize that you are not necessarily responsible for reproducing what I'm doing up here. Let's look at our old friend methane. Well, as you recall, when we draw or when we do the Lewis structure for methane, we get this. Of course, everyone is clear on the fact that that ends up having 4 electron domains. Therefore, we're going to draw a tetrahedron. Okay. Well, what are the bond angles in a tetrahedron? Everyone together now. 109.5. Very good. You just took a quiz on that. Oh my gosh. Okay, 109.5. Well, how does that explain the fact that carbon has four valence electrons, right? Carbon has 4 valence electrons. But if this doesn't explain that, but because doesn't it appear that each of those 4 electrons is in a different position, separate. Whereas here, 2 of them are together and 2 of them are separated, right? This doesn't explain this, 1, and it definitely doesn't explain this in any way whatsoever. So what can we do to kind of explain this? Well, remember, with an s orbital spherical, has an infinite number of positions available. P orbitals are 90 degrees away from each other. If we blend those together or hybridize those, we can possibly create different angles. And that's what we're going to do on paper. So, we're going to first promote, energy speaking, this electron up to the 2pz orbital. Okay? Now, when I say promote, this is at a higher energy, so it's going to require some energy to do that. Okay? But so now we have 4 separate orbitals with 1 electron in each. But that doesn't explain the bond angle piece, the 109.5. So these things are going to blend or hybridize together to form 4 separate but identical orbitals, each with 1 electron in each. And notice energy-wise, they're in between the S and the P, because again, they blended together. Okay? Here's where, once again, the people that have thought of this stuff got incredibly, creative, as as so many scientists can be, and got very, with the name of this. And we want to take a stab as to what they call these orbitals, each one of them. Good guess. They were formed from what? An S and 3 P's. Therefore, these are called sp3 hybridized orbitals. Okay, because they were formed from an S and 3p orbitals. That's pretty darn creative, isn't it? So now we have 4 separate sp3 hybridized orbitals, all of the same energy, all with 1 electron in them apiece, that can now get as far away from each other as they possibly can in a tetrahedral arrangement. So, that column that you just created on the left-hand side, you've titled it already hybridization, right? If you go down to 4 electron domains, guess what type of hybridized orbitals all tetrahedral molecules we're going to use? sp3. Okay? So if you go down the column to 4 electron domains, any molecule that uses 4 electron domains around the central atom is going to be sp3 hybridized. Now, I'm only going to go through a few of these today. Oh, I was going to draw this. Let me do this. Now, if we think of orbitals, and I've tried to show this before, these kind of like take up a lot of space filling kind of ideas, almost like balloons. If we were to draw, and again, you will never have to recreate this, darn it. again, I'm trying to throw a show a three-dimensional kind of idea here. Okay? If we think of the regions that electrons, the orbitals, if we blend an S and a P together, we would get possibly a shape that looks like this. This would be sp3 hybridized, sp3, sp3, and sp3, each of them with one electron in it. Okay? And remember I was talking about methane. What type of orbital does a hydrogen ion or hydrogen atom have its electron in? Hydrogen only has one electron. It's in an s orbital. What's the shape of an s orbital? Spherical. So if we draw a sphere to represent the hydrogen 1s orbital with an electron in it, remember I said bonds are the overlaps of orbitals, so we're going to have 4 of those. Okay? That's kind of a space-filling model that you would get for the methane molecule. Overlapping the s and the sp3 hybridized orbitals, sharing these 2 electrons, or spending time in all those positions. Okay? All right. Now, one of the other molecules we studied early on was this, BCl3. If we do a Lewis structure for that, you may recall we ended up with this. With how many electron domains around the boron? Just 3, okay? So how do we explain this type of bonding, in which we have 3 identical orbitals at 120 degrees together, or away from each other, instead of the 109.5? Well, we can use this idea of hybridization to explain that also. Remember, boron in a valence shell has a 2s orbital and a 2px orbital occupied with an electron, just one electron. But remember, we also have the 2py available also. Well, here we have 2 separate orbitals, whereas we need 3 to complete this. So once again, this electron is going to get promoted, energetically speaking, up to this orbital. Okay? So that now we're going to blend or hybridize those 3 orbitals into 3 identical orbitals, each with 1 electron in them. Very similar to what we had done with the carbon in the sp3 hybridization. Anyone want to take a stab as to what we're going to call these orbitals? See how easy that is? They're sp2 hybridized because they're only using 3. You're always going to start with an s. You're always going to add the number of p's to fill out the rest of them. So in this case, it's sp2 hybridized. We can explain that drawing, or with balloon drawing once again. We'll make an sp2 hybridized orbital here, one here, and one here, each with 1 electron in it each. And if you recall, chlorine has 7 valence electrons. I'm not going to go into all the details here, but you guys may remember making a electron dot symbol very similar to that. It has 1 extra electron. As it turns out, chlorine is also sp3 hybridized, but that means that its 1 orbital will be providing that position right here. And once again, we get that, so there's 3 different chlorines. 3 of those sp3 hybridized orbitals have a lone pair of electrons in them. The other one is used for bonding purposes. So that's how we explain the boron trichloride. Now, interestingly enough, there's another way we can come up with sp2 hybridization. And this will also, for the first time, explain multiple bonds for us. If we look at Here's a molecule that we looked at really early on when we were first learning to draw Lewis structures. You may or may not remember this. It's formaldehyde. Does anyone remember bringing this up? Okay, to draw the Lewis structure, we ended up with this. I'm not going to make you guys do it because you already have it in your notes somewhere. How many electron domains around that carbon? 3. So once again, we're expecting a 120-degree bond angle. Well, we're back to carbon again. Remember, carbon has valence electrons in the 2s, in the 2px, and the 2py, with an empty 2pz orbital available. 2 electrons here, 1 each there. Once again, we have to come up with 3 separate positions for electrons, each with 1 electron in each. This is not going to do that, so we're going to promote, once again, one of those electrons up here. Okay. We're going, since we only need to make 3 domains, we only need 3 orbitals. And again, what are those going to be called? sp2 hybridized, 1 electron in each. So I've used this one, and this one to make the sp2 hybridized orbitals. What do I have left? I still have an electron in an unhybridized 2pz orbital. We'll get to that one here in a second. Now, to make this, I only need to make, once again, 3 connections. Okay, so this is sp2 hybridized, this is sp2 hybridized, this is sp2 hybridized. Boom, boom, boom. The hydrogens are going to be easy because, once again, very similar to the methane, they just have an electron in a 1s orbital. How do I explain the oxygen? Turns out oxygen is also sp3 hybridized. I am not going to go through how that occurs. If you would like to do that sometime outside of class time, we can do that. But what's going to happen is 2 of those are going to be occupied, 2 of those orbitals are going to be occupied by lone pairs of electrons. The other one is going to be here. Now, here's the thing. I have used up my 3 sp2 hybridized orbitals for the carbon. But remember, I still have this available. Where's that electron? Well, it's in a 2pz orbital. And since carbon is also sp2 hybridized, it's also going to have a 2pz orbital with 1 electron in it. Now, any bond has how many electrons in it? 2. There's sharing of electrons. Okay. What's going to happen is, you may have always wondered, how does this double bond come about? Here's what goes on. Those 2 lobes of the p orbitals that are unhybridized are essentially going to, I'll use this, overlap each other. Okay, so they're going to kind of blend together. And that's how we get the second bond. Now, you're kind of looking at that going, wait a minute, there's 3 there. I'll give you an analogy. You guys have eaten a hot dog before, yes? With a bun. 1 hot dog, 1 bun. How many layers are there? There's 3. There's the hot dog and the top and the bottom part of the bun. Right? 1 hot dog, 1 bun. What I'm trying to say here is, this is a bond, obviously, clearly. This is a bond that kind of wraps itself around that other bond. You guys following there? Just like a hot dog. So this would be like the hot dog, this would be like the bun. That's how you get a double bond. The double bond becomes from a hybridized orbital and an unhybridized orbital. Their names are as follows. Any bond between hybridized orbitals is called a sigma bond. This is that little thing on your quiz that you canceled out. And the symbol for sigma, you guys may or may not know from your math classes, is that. And the unhybridized orbital bond is called a pi bond. As it turns out, you guys already know, I hope, what the symbol for pi is. So, when you look at a multiple bond, it is always formed from, it's going to be always formed from one sigma bond and one or more pi bonds. So if I'm looking at this molecule, this is how you would have answered the question on the quiz if you had given this one. What would be the hybridization around the carbon? Well, there's 3 positions, so it is sp2 hybridized. 3 positions, S, 2p, okay? How many sigma bonds? Well, remember I said sigma bonds are formed between hybridized orbitals. Is this a sigma bond? Is that a hybridized orbital? Yeah. Is this a sigma bond? Yep. And is this a sigma bond? So there's 3 sigma bonds. Boom, boom, boom. What's left? A pi bond. So there is 1 pi bond. So in that molecule, the carbon is sp2 hybridized. There are 3 sigma bonds and 1 pi bond. That's how I would answer that question. So on your chart, carbon has 3 electron domains. So you follow that column that you made, the hybridization column, until you run into 3 electron domains. And you will see, and I want you to write that those are going to be sp2 hybridized. So far we've determined that 4 electron domains undergoes what type of hybridization? sp3. 3 electron domains undergoes sp2. We've learned that piece. We've learned how double bonds or multiple bonds can form, and we've also learned what sigma and pi bonds are. I know that that's quite a bit here at the end. Again, you will never have to reproduce any of those drawings. I will never ask you to interpret one of those drawings. But the only thing I could do to explain what all that stuff meant to you, or meant, is to do all that stuff. That make any sense? Okay. When we come back next 82 days from now, what I'll do is I'll pick up from here. We'll actually look at triple bonds. Now I also want to look at how you can form the trigonal bipyramidal and the octahedral molecules of the orbitals. Perfect. Hey, I apologize for not having anything for you guys to work on over break. I know you're crushed.